just need to move my camera so that we can have a look at today's work.
So it's upside down. Oh, there we go.
It was, but I have fixed it. Okay, so I was going to stand in my kitchen again and use my funky whiteboard on the wall, but then it turned out that my funky whiteboard on the wall is the greatest thing my children have ever seen. And they've spent most of the last week drawing all over it, various pictures, some of them quite evil. And I'm not allowed to touch it, apparently, under pain of death. So not my whiteboard anymore. So here we got little ones instead. So I've written a couple of bits out. So we're going to talk about the de Broglie equation today. So let's make a start. De Broglie, remember, is talking about matter. I am going to reinforce this point so many times today, you are going to get very bored indeed. Matter, electrons, protons, molecules, people, absolutely 100% entirely not photons. I can't say that enough. Not photons. This is matter waves. Okay, so de Broglie is claiming that matter waves have got reality, just like energy waves are like particles. Particles can be like waves. So these are matter particles behaving like matter waves. So if I have a piece of matter, an electron, proton, atom, whatever it is, something that you would regard as being substance rather than energy, if it has momentum p, then the wavelength of its corresponding wave will be inversely proportional to that momentum p. That's his equation on the left-hand side. Lambda is inversely proportional to p. No, I don't know why we use a p for momentum, but there we go. Constant of proportionality, when the equations are done, sets the units appropriately between momentum and wavelength, distance. And it turns out that the constant of proportionality that we need to use is our friend Planck's constant. So sometimes you will see the de Broglie relate. By the way, that's obviously spelt Broglie, but it's pronounced de Broglie. So you'll sometimes see it written as h over p, and sometimes you'll see it written as h over mv. P is just mv, the momentum. Shall I say it again? This is the wavelength and the momentum of particles and waves of matter. Electrons, protons, atoms, molecules, people, cars, planets, not photons. That is not the wavelength and momentum of a photon. Okay. I'll give you a second to finish writing that down. Just stick a quick done on the chat when you're ready to move forward.
Done.
Very good. Okay. Now, when we come to be using the de Broglie equation, because we're dealing with things like electrons usually, the experimental data that we are given that we need to feed into this equation is quite often not the momentum. We regularly do not have the momentum of the particle, and we have to calculate it. And the reason that we don't have the momentum of the particle is because the machine that accelerates the electrons and gives them their momentum is that device that I've been referring to as an electron gun, which I'll show you for real when we get back in class. I thought you'd seen it, but I'll make sure you do. There's a schematic of it in your textbook in 13.4. So if you've got that in front of you, you can remind yourself of a quick picture from the video that we watched yesterday. But basically, this electron gun, the thing that accelerates the electrons and gives them their momentum, it's based upon plugging it into a power supply that has a particular potential difference. And so usually what we have is not the momentum, but the potential difference of the power supply. So the potential difference of the power supply, V, capital V now, I'm going to put little hats on it so that you can distinguish it from the velocity. The potential difference of the power supply are the joules per coulomb, and an electron is the proud owner of E coulombs, 1.6 times 10 to the minus 19. So we've regularly got a voltmeter reading, so we know V, and we know that the charge on the electron is 1.6 times 10 to the minus 19, which means that we know full well that as the electron passes through the potential difference that's accelerating it, and it escapes from the electron gun bit and travels off towards the screen, we know that this is the amount of kinetic energy it's got. So we regularly know what the kinetic energy is, and we just need to turn that into a momentum in order to feed it into the equation and calculate the wavelength. So I'm just going to go through that with you just to make sure that you're crystal clear on how to do it. So you can see that kinetic energy is a half mv squared, and you can see that there's an mv hidden inside there. So I just wanted to point out to you that if you double the kinetic energy, so 2 lots of Ke, that will get rid of the half and give us the mv squared. And then if we multiply through by m, then that will give us an m squared v squared. And so if we then square root everything, we end up with the square root of that, which is mv, which is p. I just wanted you to see that because it comes up a lot. It's very rare that you have a question in which you actually know what the momentum is. So quite often, the version that you're actually calculating with is that one. Now that one is not on your data sheet, and you're unlikely to remember it so that you can whip it out in an exam. So you just need to be clear on the manipulation here, just so that you can turn the kinetic energy into a momentum, ready for putting into the equation. So again, just give me a quick done on the screen when you are ready for me to move on. Frank is done already. So's Kira. Right, let's move on further then. Okay, so this is your page in your textbook that we have got as far as now. So everything that I spoke about, well, not everything, but the examinal bit of what I spoke about yesterday and today is there on that double page spread. And if I go down a page. There's a little bit of the derivation that I just spoke to you about for the kinetic energy. And then really all that remains is for you to practice using the equation to make sure you can actually put numbers in and get an answer out and get some familiarity with the wavelengths of some material. So in a moment, I'm going to leave you to do those questions. But just before I do, I just want to do a quick summary of this fairly quick quantum topic. So that's what I'm going to move to now, just a quick summary. And then when I've done the summary, the bit that I just need you to return to is doing those 6 questions there. So let me just stop that again. Okay, this is a summary of the equation-y bit of the topic. So we've got 3 equations in this topic. That's it, the whole topic in 3 equations. So this one is photons. This one's electrons, or any other bits of matter. And then this is where the 2 come together in the middle for the photoelectric effect. But even then, it's the photon bit that's going in there. We are not producing any, or we're not talking about any electron waves that are coming off. We're talking about the electrons themselves as particles. The most common mistake that is made in this topic is to muddle up these equations when you come to calculate, or to forget simple things from other topics, like to remember that you can flick between frequency and wavelength using the wave equation, or that momentum is actually m times v, or that you can express it as kinetic energy, or to forget how to use this equation to remember that if the kinetic energy is 0, then that means that this photon energy is actually equal to the work function, which is a way to calculate how big the work function is. And in fact, when that's the case, we sometimes put a little subscript of 0 on this F here to represent what we would call the threshold frequency. So even though there are only 3 equations, the manipulation of them is sometimes just badly done. So just be careful. Don't get lulled into a false sense of security that just because there are only 3 equations, that there's not some complexity here. There is. And if I could just enforce yet again, one more time, because I am tired of students getting it wrong. This equation here, the Einstein-Planck equation, it's called the Planck equation, but it's due to Einstein. This is about photons. This is the frequency of a photon. This is the energy of a photon. And then this equation is all about matter, in particular, mainly electrons most of the time. This is the wavelength and momentum of an electron. You cannot use these 2 equations together ever. This one is for photons, this one is for electrons. If you ever answer a question by using both of those equations at the same time, I don't care how wonderful your work is, you have done it wrong. There is never an occasion where you need both of those equations at the same time. Never glue them together. Never take the wavelength from here and start stuffing it into the frequency here. That is the most common mistake Year 12 students make in this topic, and it is absolutely wrong. Honestly, I cannot say it enough times. This is a photon equation. This is the wavelength equation, and they must not be married together. Max, you will not get it right, and even if you do, it will be utter fluke, and you won't get the working out marks for it. So, that is my most important comment. Yes.
In the photoelectric equation, what does the phi mean again? Is that the minimum?
Minimum energy. It's the work function. It's the minimum energy required to release an electron, and that electron will need to be a surface electron, because any electrons deeper down inside the lattice will need more energy than that.
Okay, thank you.
Okay. On top of those 3 equations, there was the only other examinable part of this topic really was the articulate in words how the photoelectric, well, what the photoelectric effect is and how it is explained successfully by the photon theory of light, but it is not explained at all by the wave theory of light. So we've had a practice, I think this time last week, at having a go at that. And you should probably make sure before you put this topic to bed that you can still do that. So 3 equations and an explanation is the entirety of this topic. However, I've tried, while teaching it to you, to give you a couple of lessons as well, just on the weirdness of quantum mechanics. And I've tried to give you a little breadcrumb trail of how you can find out more if you're interested. And then just to give you a heads up that towards the end of year 12, usually, we'll see how this year goes, whether it's any weirder than it already is, but usually towards the end of year 12, we return to these kind of ideas as we begin the year 13 course at the end of the summer term. And we will come back to this and we'll talk about particle physics, and we'll pick up the theme of photons and waves of matter when we get onto the particle physics topic. So this is just a quick introduction now, and we will return to it later on. But if you want to read about it, please do. It's exciting and interesting, and if you are interested, feed that interest. Okay, so for the remainder of today, your goal is to complete your notes, check you can still express the photoelectric effect explanation, but before any of that, answer questions 1 to 6 from 13.4. I'm going to suggest a consolidation lesson next week to do some exam style questions. And so if you get stuck, you can ask me anything then. But if you know already that there's something you're stuck on, you are welcome to ask it now. Otherwise, you are free to leave if you wish to and get started on those questions.
Thank you, sir.
See ya.
Cheers, sir.
Bye.
Right, thank you, sir. See you later.
Bye, Zach.